Our next speaker is Omar Ulises Reyes Amador. The title of the talk is Towards and Observationally Without Any Velocity Torus Models.
Hello everyone, my name is Ulises Reyes. I am finishing my PhD in the Institute of Astronomy and Statistics here in Iran. And I'm going to talk about my PhD project, which is about radiative transfer models for the hospitals in AES with the supervision of Jacopo and Omar. Okay, I wanna skip this introduction because the previous talks have talked about it. So I'm going to start with the type of methods of the techniques that we can use to study the velocities. For example, in this case, we're using the SDT in order to derive some physical properties of the torus. For example, the chemical composition. In this case, we can see some work that have attempted to determine the chemical composition of any samples. For example, in these works, they have used some loss species to fit the silicate features. And in the other hand, we can see some works that have different grain sizes or different compositions, like polymer and carbon, etc. This kind of techniques, most of them use analytical models only to fit the spectra of APNs. But also, we can find in the literature a lot of analytical models. The previous talks have mentioned some of them. We can classify them based on the dose distribution. We can see the smooth models, two-phase models, lumpy models, and those that also explore the geometry for the torus. We can mention the disc closed-wing models. And all these have different assumptions for the dose distribution, chemical composition, or grain sizes, for example. And they have used to reproduce the observations in the different epochs. For example, in this case, they were the first ones to prove, for example, the unified model or the observations of that epoch. But then, when some objects were observed through the interferometer, for example, and this polar emission was observed, this kind of models started to be used to reproduce observations. So in this work, there have been some work that have attempted to compare these models with observations, and most of them have tenets that, for example, a smooth distribution is better to reproduce the spectrum of different class of objects. For example, in this work, the of Mayra in 2019, they found that, for example, the gloppy models are better to reduce the Zipper2 and the disk and wing models better work with Zipper1. And another work, the 2023, they created a grid of two-phase models with this lumpiness, and also they studied the role of the grain size in the chemical composition, found that, for example, when this model is implemented in the sample, it's better reproduced in the zero spectra. So this suggests that the composition in the dust have to be grain with higher sizes. So another course have compared models versus models in order to see what are the effects of the dose distribution. And in some work, for example, this one of Felter in 2012, They try to compare smooth versus clumpy, but since the models were created with different approaches, they don't have much parameters. So this is a problem when we want to compare models. Another attempt to compare models versus models, focusing in the potential distribution, is that done by Zalewski, but he only focusing some fixed parameter values. Okay, so my work is motivated by these different models that have to reproduce the observations, assuming different chemical composition and other parameters. Because when we use these models and we compare them, all these differences are not considered as bias in the results. So in this case, we wanted to do is to create a complete of models using the three loss distributions, using the same rapid transfer code, but also exploring an observationally motivated loss chemical composition in order to implement it to these RT models. So my work is divided into two parts. So this part is trying to determine a loss chemical composition, and then we implemented this result to the transfer models in a model grid. Okay? So I'm going to present the main results. If you want, you can ask me about the method and that stuff. So in the first part, we found that the composition that then reproduced the spectrum of sample where AGN, Zihuagn, Zihuagn nearby against, we found that the best composition is composed by these four species. You can see torus alumina, olivine, pericles, olivine rods of a great size of 3 microns. And then we calculated the mass fractions of these species, obtaining these percentages when only the fraction of silicates is considered. Here we have to include also a fraction of graphites. And only to see what happened when we compare the synthetic sets using this chemical composition, we can see here the residuals. In the top panel, you can see the best fits. In the middle panel, you can see the best composition that is composed by these four species that I mentioned. And in the bottom panel, we can see what happened with the residuals when we use only those silicates that are implemented in the models of the literature, which is the composition of the terrestrial. And we can see that this composition is better than. Okay, so the next step was introducing this composition to the variety transfer codes called skirts. And you can see the web page if you want. And you can see this all different compositions that we can the model that we want to simulate in this codes. And in our case, we created a model, a grid of models with this parameter space. We varied for example, the optical depth, the dot distribution in radial direction and polar direction, opening angle, the size of the torus, the filling factor, and the lumpiness. So this is the three different dose distributions, but in the case of two-phase, we use four different lumpinesses. Okay? And also, we use two different dose chemical compositions. In this table, we can see the composition from the previous work. And in the bottom, we can see a composition that is based on the Gonzalo Martinez that 2023 work that obtained that a good composition for gens is the same as the interstellar medium, but using larger grain sizes up to 10 microns. On total, we analyzed this number of synthetic cells, and just as an example, you can see here only one model in two different compositions. Here you can see the composition of my core, and this is the composition based on the interstellar medium. And just to highlight some characteristics, you can see that for type 1 cells that are the glucose, you cannot see chemical features, so strong, both definition or absorption. But in the type 2 cells, you can see strong absorptions for both silica features at 10 microns and 18 microns. On the other hand, with the cellular medium composition, we can see strong silica diffusion emission for the type 1 cells, and also strong silica diffusion absorption. And if you see the different panels, you can see that the lumpiness is larger to the right. Okay? So this is smooth, this is lumpy. This is nice. And this is only the coverage of all of our synthetic cells, just to see what is the fluxes that are covered by your model. And just to mention the main results, where we compare models versus models, we can see that, for example, the smooth ones compared to the two-phase with lumpiness of 25% and 50%, the differences are negligible. And the same happens when we compare lumpy with the two-phase with a high lumpiness. And also, if we see the residuals between smooth models and the counterparts, or lumpy models versus the counterparts, we can see that in the H1 view is the highest differences between them. And here we can see what happened with the filling factor in the left panel. And we see that this parameter is not sensitive between the different node distributions. And in the right, we can see what happened when the lumpiness is different. And we can see that in the case of H1 cells, the differences are very strong between the different lumpinesses. And in this part, we can see what happened when the non-structural composition is different. And we can see that also in H1 sets, the differences are very high between the two chemical compositions. And also, we compared with observations using these parameterizations of the spectra, using the slopes or the properties of the silicate features, just to do it like in the past when the spectra were not available, only photometry. And we can see here in a general view that the chemical composition in the interstellar medium is more, it tends to be more in the parameter space of the observations, and also it's better for a lumpy distribution. And also we use the chi-square technique to compare the spectra with the observation, the synthetic set with the spectra, the observed spectrum, and we obtained that also the models with these lumpinesses or highest are able to reproduce better the observations. And also we saw what happened with the type 1 or type 2 sets, and we obtained that, for example, when using my composition, the smooth models are better to reproduce the type 2 object, the type 2 sets, and with the other composition, there's no difference between type 1 or type 2 to reproduce observations. And as a future work, we want to include the polar dots to the models in order to study the effects of the wind in this kind of random transfer models of the torus. And this is all from the
Questions?
Thank you for this amazing work. So, did you test any of the resources, not only this numeric base and your proposed mass distribution? Composition. So, because I saw that some of the things are seen that we see in the business. So, it's working to double check these compositions very accurately.
I have not done that. I only use the Zihuagn as two objects, but yes, another idea is to compare my models with another class of AGNs, for example, the quasars or these logically big AGNs, or maybe the units that I mentioned, in order to see if my composition reproduces that spectrum.
It's very different, I think this.
Yeah, because as you can see, my composition produces strong CDS diffusion absorption, and this kind of features are observed in fluids, as you mentioned, and in other dynamics.
Maybe I just pay attention, but one thing I was wondering about is street. I understand that the new chemical composition helps in representing the AUC, but can you at the same time rule out that the different geometry could also explain? So I don't know, how do you, is there any possibility to break the degeneracy between the geometry and also the
That's a good question. In this work, we cannot do that because the time of my PhD. Because if you want to include, you want to include composition in the grid of the rectangular models, it increases exponentially the build time. So, what is the ideal method to do it? Because if you divide in implementing first technique that was an analytical model to obtain a linear composition, when we include to the radiative transfer, the results are different. And it's difficult to break this degeneration.
Thank you. And then it's following on that. If you go back to your multiplication fraction of the second phase, yes, so you're still in the low 20s, 50s, so you're still not fitting well in most of the sample. So you have infinite time in your PhD. I want to explain this. How do you really improve this to go more? Is it really just the composition, or is what is the missing part of giving you a most acceptable fix for a large percentage?
The number of parameter values that we explored can be larger. In this case, we only explore 3 values for each parameter. Except for the picobet, it has 6 parameters. But if we increase the parameter values in the grid, maybe we can obtain more as of this. Thank you.
Okay. If not, we can pass to the next talk. Experiences. Next speaker is coming Sykes. He talked about the RSP simulations of stochastic torus scaling equation.
Okay, hi everyone. I'm Karen, and I'm going to talk about some modeling. Oh, I need my phone, yes. Okay, hello. Some quick motivation. I think we've already seen this diagram twice so far. Agent environments are complex, dynamic, multi-phase, and fully dynamic simulation is like a great way to capture that, but obviously at the cost of a lot of computational time. So I think it's difficult to do these really filtered parameter searches with simulations, but there's still a really good tool for kind of validating these in a qualitative sense. The way we intended our observations. And so in particular, we have this sort of punitive discipline model or explaining model. And what this work is about is trying to see if we can sort of reproduce that without sort of like imposing it at the start, so without sort of deliberately trying to make that geometry. So technical details, I want to skip over the main thing that's not all about what we do here is we explicitly calculate the obscuration from the AGN to all the gas within the simulation. And so we can then use that along with a big group of models from cloud, which is a photo efficient code. So we can use that to build a big lookup table for all the thermodynamics, heat rates, flow rates, capacities, and hence the rate of acceleration of each part of the field. So we directly capture the rate of force from the AGN on the gas. We're trying to build a torus. What is the setup for this? So we basically have individual discrete clouds, which are sort of like a rough model for a jump cloud. And so we generate them on sort of highly inclined orbits that take them into the central region and specify a particular rate of sort of time average accretion. So once those clouds fall in, we have a fairly low luminosity AGN, which is just a computation condition, basically the high internal luminosity, the stronger acceleration, the more computation time it takes to happen. So once it starts accreting, that switches on, it starts driving an outflow, and we let that run for a certain duration, which is like the active accretion phase. And then after, it works out to about 5 years. Then just after that point, and then switch off any further accretion, but we let the simulation keep running and basically see what happens. So bottom line is, what does that look like? So time goes from left to right, and the top panel is just the gas density, and then the gas and dust temperature. So to start with, you can see all the clouds falling in, and then they start to build sort of this in the middle, and you can see lots of sort of elementary structures surrounding that. In terms of the gas temperature, so you can see there's initially a sort of once the engine switches on, it sort of quickly heats the outer clouds. So you get these sort of expanding bubbles, which eventually overlap, and you get this volume filling hot phase, and then you can sort of see that there is this cooler sensitiveness. And similarly in the dust temperature, so you can see we have cool clouds coming in. Meanwhile, in the center, you've got this sort of small region of a lot of dust. So before we go further, one thing to discuss, which is the fact that because these simulations are sort of optimized for a relatively large domain, like a sort of 50 parsec size, we don't reliably capture the sort of very small scales around the sort of measurements. So we do need to sort of include a model for unresolved observations happening on those scales. And so the previous postdoc in our group did sort of similar simulations but on this parcel scale domain. And so basically just based on doing a sort of simple parallel fit to those, we have this sort of analytic term for the unresolved obscuration. And then also, yeah, the other thing we have is just from sort of purely geometric arguments, there is an angular dependence of the intrinsic flux on the AGM. So just by working out, you know, what's level of visibility you have of the conditions. And so depending on what we choose for this this parallel or intrinsic absorption, we do get some qualitatively different results. So I'm still working on what the right answer is for this. So if you want to ask me about that, do. But for now, we just pick one model, which is the blue line, so subgroup thing. And so now moving on to what outflows we see. So this is just the radial velocity of the gas, so not any line side effects, but so obviously to start with, you can see the strong influence signal from the clouds that are falling in. And this is now time, it's just running like left and right, and then again on the second row. And then so as we proceed from this initial active phase to the passive phase, where there's no longer new clouds. You start seeing this quite distinctive signature where you've got the strong polar outflows, and then you've actually got inflows close to the equatorial plane. What these are is they're basically tail winds. So gas that was not efficiently vertically accelerated, didn't reach escape velocity, sort of followed into orbit to come back into the AGM. We can also look at the properties of the outflow. So I guess the main thing here is, so the top left is the outflow velocities. So there's initially this very large spike when the AGM first turns on. The bottom left, meanwhile, we've got the outflow rate. So this gets up to, so the inflow rate we specify 1 kilomass per year. So the outflow peaks at about 20% of that inflow rate at and the way I visually is I just sort of consider spheres are different. So spheres centered on the AGM, right? And I just look at how much material is passing through those spheres and what the properties of that material are. So we see that in the innermost sphere, which is at 30 parsec, there's this sort of very stochastic behavior. But as you go out to larger spheres, you see that the sort of total outflow rates drops overall. So you don't perhaps this is another sign of these state limits. And then physical properties of the outflows. So it's mostly warm ionized material, and density drops as you go outwards. So the other thing we can look at is so this is basically just the column density CTAGN along different polar angles. What color correction is. And so here the axis is the polar angle, and then the sort of error bars are just the sort of range in the azimuth direction. And here, so I'm showing the 4 different models for this subgrid obscuration, and there is scatter, but the general trends are similar. So there's always high obscuration, sort of in the full direction of the wind, and in the models where there is more subgrid obscuration, what this also leads to is you end up building a massive disk in the equatorial plane, which also contributes to obscuration at low altitudes. And speaking of which, so here's this. So this is again going forwards in time as you go along the roads. So to start with, you can see it's very chaotic. So as we were talking about, we have the infalling clouds that can efficiently disrupt this. But once that infall stops, and you start getting cloud winds that are re-entering in the equatorial plane, and doing the water depletion, this can then start building this sort of 10 parsec radius disk. And then as we go to the end of the simulation, the sort of supply of this failure material is outside the drop, same time, the AGN is continuing to drive outflows from the disk. So you can see that the sort of the amount of mass of this is then gradually sort of being removed by the radiation pressure. Okay, here's just so for the second row now showing the dense current row as well. So you can see that we have this some cool dense disk which has cool gas in it, and then even though there's very little friction, there's hot material. So we've now moved on to some observations. So this is for the final, so for this, at the very end of the simulation, this is now basically predicting the emission map in some of these lines. So you can see it's kind of as you expect. So the CO traces the disk, and then some of the other lines trace then kind of high intensity regions in the middle. And then we also have this C1 line, which is sort of sensitive to slightly lower density, hotter shot material. And that will do is we can actually go back in time. So this is now at the point where the disk reaches its maximum mass, which is about just less than 2/3 of the way through the simulation. So this is when this sort of re-accretion along the equatorial plane is most efficient. So you can see that we have this development and stronger, but also more spatially extended emission in some of these lines. We do the same thing for the vapor hydrogen lines. So this is now on a, so the previous plots were like on a 10 pascal scale, this is now zooming out a bit to 50 pascal scale. So here you sort of start to see it's picking up these kind of filamentary features of accretion. And again, if we rewind time a bit, we go to this point where the disk is the most massive, you can see these strong and filamentary features. And so this is both tracing the activity distribution of gas, but there's also very, I say, short time scale, it's variation of, if you like, the weather at the very smallest radii. So I say short time scale is actually about 10,000 years, is kind of finest time resolution I have. So unfortunately, it's not something you can literally see in the but it does mean that there is this big diversity in what the sort of distribution of emission is expected to be. And then finally, we can also predict as well as the lines we predict zero amounts. So this is going all the way from 8 nanometer to 2 micron on the left, which we don't really resolve on us. As I said, it's we don't really resolve on us. It's sort of on 2 small scales, so the sort of sensitivity is very low. But as we sort of go out, we sort of trace the inner regions of the output cone, and then as it goes along the way, we can see that starts to cut the dead central material in this. So that is actually basically it. And so I just want to kind of conclude by saying here's another attempt to sort of make sense of the different observational features you see by synthetic. So I can't do the H2O but here's sort of all the other bits. So we have the kind of the short wavelength in the innermost regions, going out towards the mid-IR, we trace the sort of inner parts of the output cone and the inner parts of the disk, and then going in some millimeter, we then pick up this statistical quality. And so put it all together is my attempt to the course. Thank you very much.
Yes.
Very nice work, Colin. My first question is, what's the physical origin of your outflows? And the second question is, what dictates the inner radius of your what do we call it? Is circularization?
Okay, so by sort of physical origin of the outflows, you just mean what process is driving them?
Yeah.
So it's just the direct radiation pressure force from the AGN emission. So the big bit of physics that isn't in these is magnetic fields. So I can't say anything about those, but this is just purely the degree again. And then yes, so we go back. So you can see the disk is kind of, or I call it the disk, it's more like a donut really, is growing out with time. So that is just the radiation pressure is sort of gradually upgrading its cavity, so it's pushing it radially outwards. So an interesting thing I've not looked into yet actually is what the velocity profiles of the disk are, so whether it's subcapillary and actually supported by radiation, or if it's mainly capillary and really what's just happening is that you are eroding the inner edge by blowing it away from it. So I'm not sure the picture those two might be.
Yeah, so I just now part of my answer. So this whole you see there is real. It's not caused by you being limited in your resolution. Did I understand that correctly?
Yeah. So in theory, this one is real. There is a sort of limitation on how close to go. It's more like 0.1.
Yeah, because I'm surprised. I don't know about H2 line, but on the molecular lines, you also see a clear hole. So per second. Yeah, exactly. And I don't think that this is being observed in that sense in the data. There's really this one. The CO is a separate question, but the dense traces are not aware that there is such a clear hole being observed. So that's something where the model might have to be adjusted a bit. My question, and related to this is, what's the prospects of possibly combining the higher solution conditions with the lower scale conditions? Going all the way down this.
So on the point of whether it should go all the way in, so this is something that seems to be quite sensitive to what we assume for this sort of unmodeled observation, because the intrinsic depth. So that is something we need to sort of figure out. As far as going down to smaller resolutions, it is something I'm working on. At the moment, it's just a technical how we do it efficiently. Basically, we have a sort of inherent. We're probably going to talk about that. It's not really about. It's about the way. If you're interested in that, then we can talk about it. But it is in theory solvable. It just requires some examples.
Such a great talk. So can you continue going to water wavelengths and start talking about like radio continuum too? Is how far does this go?
So in principle, yes. So basically the big grid planning models that I run, that's where I extract the limits and capacity that you need to calculate maps. So that covers principally the entire manufacturing. Someone that knows more about radio than I do might be able to tell me, what processes are important. I don't know, synchronization and that sort of thing. Or so there's no explicit modeling yet, so to say. Right. So I don't know to what extent that would actually
I was thinking about having shots and stuff together around like individuals. Are you able to like various sorts of generality having where the shots would be occurring in the system too?
In principle, yeah. I think so, yeah.
I'm asking this, what representing the size of the form of the evidence, we do not see such options. There's some category, but that's more. Yeah.
Is it like classic scale or not 10 times, yeah.
And the second comment is that we found that one by calculate integration and radar ordinance. And to what extent did the also get some mode of calculation? Because we see in some of the small tests that accuracy is taking place in the plane of the galaxy and it's driven directly towards the first part of the towards. You think that this will change the results?
So potentially, yeah. The kind of argument we made was that whatever happens out of sort of kilometre scales, perhaps by the time that gets into the AGM, you would still expect the kind of distribution of powers to be isotropic. So I think if there are, but yeah, as you say, there are things like you might expect to sort of deliver like a sort of stream or whatever. And I think, yeah, it would be interesting to just model that. I think the sort of interesting thing we see here is that the kind of chaotic vision plane is chaotic even on these sorts of scales. And it's actually once you have enough time elapsed, basically dynamic time for wind to come back in, which are then much more ordered. That seems to be then when the sort of this formation really takes off. So to what extent those interact. We really think sort of arbitrary run for a bit, then turn it off, and obviously the real system can be much more complex. Thank you.
I saw that you started with the AGM answers 10 to the 6.
Yeah.
So masses. Have you explored the effect of larger masses on the simulation?
No, yeah. There's no reason we can't. It's sort of just a sort of thing. So if you make a mass bigger, that time for and the accelerations that the gas is go on, which means the time accelerations get shorter to the right. So again, it's just sort of optimizing the numeric so that we can run these times. But we have some of the previous work, we have sort of looked at something going to get any class or information. And there's no sort of significant qualitative differences. Probably the most significant one is if you make it strong enough, you basically just load the material up. And at that point, it's sort of a bit, so there's no material sliding to make it into the AGM's power package. But that sort of would make sense. But yeah, sort of where that threshold is.
Very vast question is mine.
So I think you make a pass about the temperature maps that I was showing.
Yeah.
Why is the temperature the last is not reaching the level?
Yeah. So I think there's probably two things. So basically, the color index is the mean of our sites. So there's a small amount of very hot gas, then you sort of wouldn't capture that.
You should see the whole simulation.
Yeah, so you should do it. I think it is basically just a resolution. So the gas, each kind of particle of gas in simulation has different size. And that probably is larger than the simulation is. So basically, what happens when a gas particle gets that close? We say it gets released. So just solve so this is like zero gravitational simulation. We would say in some radius against the
Thank you. Great. This is the last photo today. Is announcements. Thank you to all the speakers.
We can answer for the people here.